Good morning, everyone. In yesterday's lesson, we introduced Cartesian vectors, and we talked about how to do some of the basic operations with Cartesian vectors. So we did addition, subtraction, scalar multiplication, magnitude, figuring those things out. So this morning, we're going to return to the dot product, okay, and we're going to be looking at how does a dot product work with Cartesian vectors. Okay. So this first slide, we're going to work through the derivation of how to get the dot product in Cartesian form. Okay. Now, what I mean by that, okay, and you don't have to write this part down. I'm just going to flip the slide for a moment here. Okay. Depending who you had for grade 10 math, you may have seen this derivation before. This is how you get the quadratic formula. Right? You start with some general quadratic that looks like this. Okay, and then you basically complete the square on the general form, right? I common factor out the a, okay? I find half of this fraction and square it, and then add and subtract it, okay? And then I start moving things around. Okay, I'm not going to go into that in great detail, but that eventually comes around to quadratic formula. That's where it comes from, is completing the square on the general quadratic. Okay? So we are going to try to figure out the Cartesian dot product in a similar kind of way by starting with the geometric form and seeing if we can bring it around to the other form. Okay. So here we go. In the diagram, we got two vectors. Okay, I'm going to use A and B instead of U and V, just because we're going to use cosine law in a moment here. Okay. So this is A, and this is B. And I have the angle in between. So I'm going to draw a third piece over here and call that vector C, okay, running between A and B. So my first step is I'm going to write out the cosine law. Okay, because I'm talking about vectors, I have to put all kinds of magnitude symbols in here. So the magnitude of C squared equals the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B cosine of my angle. Okay. Now you may be thinking, how on earth is this going to help me figure out dot products? Well, the thing to note here is this part right here, okay, A, B cosine of theta. Okay, if you flip back in your notes to the geometric form, that's what dot product was, right? And I'm just going to jot it down at the top of the screen here. Okay, again, you don't have to write it down in your notes, but when we did dot product the first time, A dot B equals magnitude of A, magnitude of B, cosine of the angle in between them. So now that means I just need to rearrange this formula a bit, okay, and I will have another expression for dot product. Okay, so I'm going to move the expression with cosine to the opposite side of the equation and bring the C across. So that's my first step. 2 magnitude of A, magnitude of B, the angle equals magnitude of A squared plus magnitude of B squared minus the magnitude of C squared. Okay, we made some progress. Okay, so on the left-hand side, I'm just going to rename that. That is 2 times the dot product. Okay, which is what I'm trying to figure out. Okay, for the next part of this, I have A and B on the left. I have A, B, and C on the right. Okay, it would be nice if I could rewrite C in terms of A and B. Okay, fortunately, I can actually do that. Okay, the vectors are currently aligned tail to tail, right? So I can set up a subtraction statement. Okay, I didn't note which way C was going, but I'm going to pick a direction now. So let's say if I have C going this way, Okay, that means that C is equivalent to A minus B. So magnitude of A squared plus magnitude of B squared minus the magnitude of A subtract B squared. All right, so we're going to keep the left side the way it is for the moment. To A dot B equals. Okay, magnitude of A squared. So I'm going to do a little note aside again here. Right, if I want to do magnitude of A, right, that's equal to the square root of A1 squared plus A2 squared. Now, in my expression, I'm squaring that, right? So if I squared both sides, that's going to remove the square root. Okay, so magnitude of A squared is just A1 squared plus A2 squared. Okay, so that first part becomes A1 squared plus A2 squared. Okay, similarly for B plus, okay, that is B1 squared plus B2 squared. Okay, last but not least, I have A minus B. Okay, it is the same, but you know, what does A minus B look like? So again, I'm going to do a little aside here, right? When I'm subtracting the two vectors in that form, A minus B, right, how do I get that? Well, I take A1 and I subtract B1, and I take A2 and subtract B2. Okay, and I'm sorry that kind of ran off the screen a bit there. So those are my coordinates now. Instead of just an A1 and an A2, I have A1 minus B1. Okay, so the third part, let me clean that up a bit first. Okay, this was A2 minus B2. Okay, so the third part of this expression, okay, this part right here, okay, becomes, okay, so I am subtracting A1 minus B1 part, yep, that's right, squared, plus the second coordinate, which is A1, sorry, A2 minus B2 squared. Okay. Next. Okay, my left side is still the same. Okay, on my right side, it's just a matter of cleaning up that last expression there. So I have my A1 squared plus A2 squared plus B1 squared plus B2 squared. Okay, minus a big bracket here. So we'll start with the first bracket. Okay, so again, a little aside here, right? If I'm squaring that, that means I'd be FOILing it out, right? That means I have A1 minus B1 times itself, A1 minus B1. Okay, and I would start having to expand that out and tidying it up. Okay, so what I'm going to get from that first one, okay, I'm going to get A1 squared. Okay, I get A times B1 and A times B1 again, so you get minus 2 B1, B1, and plus B1 squared. Okay, for the second one, okay, I basically get the same thing, just with 2's. So I have A2 squared minus 2 A2, B2 plus B2 all squared. Okay. So we are just about there. Now I start tidying up my expression and see what I have left. So this A1 squared, okay, and then inside the brackets I'm going to have subtract this A1 squared, so they're gone. Okay, A2 squared out here, right, subtract A2 squared, those are gone. B1 squared, B1 squared, B2 squared, B2 squared. Okay, so all I'm left with is this term and this term. Okay, there's that negative in front of the bracket, so this whole thing turns into, okay, 2 times A dot B equals 2 A1 B1 plus 2 A2 B2. Okay, and our final step, after all that canceling out, I can divide everything in this expression by 2. So the dot product in Cartesian form, A dot B, is equal to A1 B1 plus A2 B2. Okay, which is a very tidy little formula now that I'm done. Okay. Really all you're doing is you're multiplying the coordinates together and then adding each of the results, right? So multiply the coordinates separately, your x coordinates, your y coordinates, and add up the results. So we're going to summarize that on the next page and do a quick example. So again, if my A is A1, A2, and B is B1, B2, okay, then the dot product looks like this. Okay, it is just, whoops, pardon me. It's A1 times B1 plus A2 times B2. So what I'd like you to do, this would be a good place to pause the video. Here are three pairs of vectors. Okay, I just want you to try doing the dot product. So take a moment, run them through, and then I'll come back with the answers when you resume. Okay. Okay, so if you come back, I'm going to go through the answers here. Okay, I'll do the first one in long form so you can see it, and then the other two I'm just going to put up what the number would be. Okay, so for the first two, to do the dot product, okay, 1, 5, dot, 7, 9. Okay, what the rule says I have to do is multiply my x coordinates together, so 1 times 7. Okay, and multiply my y coordinates together, 5 times 9. Okay, and then just see what I get. So I've got 7 here, that's 45, so our total would be 52. So the dot product of those two vectors is 52. Okay, for the next pair, when you run that through, you should get 32. Okay, and for the last pair, when you run that through, you're going to get 4 times 6 is 24. Negative 3 times 8 is negative 24. You get 0 as the last one. Okay, now that one, I'm just going to highlight for a second there. That one is interesting because in the original note on dot product geometric, this was one of those properties we talked about, okay, right? If the dot product is 0, that means that these vectors are perpendicular to each other, okay? Okay, and that's what that means. That's going to come up again in a little bit here. Okay, example 2. Okay, we're going to use Cartesian vectors to verify the commutative property for the dot product. Okay, so again, to review that what that means. Okay, commutative property says that if I have u dot v that is equal to v dot u. Okay, that's the property that I can switch the order and it technically doesn't matter. Okay, so this little proof, okay, or verification is really quick. I'm going to start with u dot v. Okay, and write out what it means. It would mean u1 times v1 plus u2 times v2. Okay, what does that equal? Well, I want it to be the other way. Now, in this form, these are really just numbers. Okay, right? It's because coordinates, it's numbers. Okay, I know that the coordinates are, sorry, with numbers, that I can reverse the multiplication, doesn't matter. Right? So I can rewrite that as v1, u1, plus v2, u2, and it means the same thing, because I'm just switching the order I multiply the numbers in. Okay, but that's the definition of dot product in the other order. So that equals v1 dot, pardon me, not v1, v dot u. So that's done. Okay, we're going to go on to our final example here. Okay, determine a value of k such that u73 and v5k are perpendicular to each other. Okay, so again, that last piece there, where it says they're perpendicular, that's a key thing. Okay, because they're perpendicular, we know that u dot v should be equal to 0. Okay, and actually, I'm going to back up a second. I'm going to make that my first statement here. Okay, right, u dot v is equal to 0. Okay, I know that's true for sure because they're perpendicular to each other. So now I start filling it in. What would I do for dot product? Well, I multiply these together. So I'm going to have 7 times 5 plus these ones. So 3 times k equals 0. Okay, so I have 35 plus 3k is equal to 0. And now I just have a little linear equation that I can solve for k. So we bring the 35 over. Okay, and now we divide both sides by 3. So k equals negative 35 over 3. So that is my value of k. Those two vectors will be perpendicular. So that's it for the Cartesian form of dot product. Okay, here's some practice work that will allow you to practice those concepts. Okay, thank you for watching, and I will see you tomorrow.